Hey guys, Mrs. D here. I just want to go over some stuff that we kind of had to stop a little bit in class today. So let's look at some of these chromatography questions. You guys have I gave you the hard copy this morning here in class, and I also put this on AP Classroom so you can practice too. But let's take a look at some of these questions real quick. First one, the diagram above shows a thin layer chromatogram. Okay, so again, the actual piece up here is called a chromatogram. And we need to first look at the separation was formed using 50% ethyl acetate in hexane, okay, as a solvent. So that's our mobile phase. Silica gel is going to be polar stationary phase, okay? On the basis of the chromatogram and the information about solvents in the table above, which of the following would be the best way to decrease the distance that the products travel up the plate? So we're trying to get these products to actually come down here a little bit. So what we have to do is look up here at the relative polarity, especially of hexane and ethyl acetate, because this is going to be a combination here of our mobile phase. So ethyl acetate is actually dissolved into hexane. So if we lower the concentration of ethyl acetate, it'll actually make the polarity less here too. So therefore, if we have a lower polarity because the silica gel is polar, so our stationary phase is polar, and our mobile phase being very polar. Okay, so if we lower the polarity of our mobile phase, then we can get these products to stop down here and have a lower RF factor. So therefore, what we want to do is we're going to decrease the percentage of the ethyl acetate in the solvent. Okay, we don't want to increase because that'll make your spots go even further and they'll probably go off the page. And pentane, there's no reason to use pentane instead of hexane because the polarity is the same. And if we add 5% methanol to the solvent, we're increasing the polarity already again. So we want to go with B, decrease the percentage of the ethyl acetate. Let's look at question 2. And I know like my head's kind of up there in the thing, but you guys have this in front of you. A student obtains a liquid sample of green food coloring that is known to contain a mixture of two solid pigments, one blue and one yellow, dissolved in an aqueous solution of ethanol. Which of the following lab setups is most appropriate for the student to use in order to separate and collect? So this right here, we need separate and collect. This process is called just filtration, and it's a great way to separate and collect if you had a solid and a liquid. The problem is with this one, we've got just simply an aqueous solution. So if we poured that aqueous solution down, we wouldn't separate anything. This is only good to separate a solid out of a liquid solution. This here is called distillation, and this is a process in which what we could do is boil. For example, we might have a solid in the solution. Say we had salt water, we could boil the water off, and it would condense, and it would condense in this tube right here. This is called the condensation tube, and then we can just get the actual pure water off of there. And let's say if we did boil salt water, the salt would stay in the bottom here. So this is a distillation process. Again, if we wanted to separate a solid from a liquid, this is another good way. This is our thin layer chromatography here. So this would just be our chromatography by paper chromatography or TLC chromatography, thin layer chromatography. And in this case, this is going to be TLC because we actually don't know for sure because we don't know what the chromatogram is made of. So this could be paper chromatography. The great thing about chromatography is you can separate to see the differences, and you can separate to see, hey, I do have more than one compound in here. However, we can't collect. So that's why this one, column chromatography, is the best. So column chromatography, you can actually separate because what you can have in here is there could be some silica gel compounds, there could be sand, there could be other mixtures in there. And so what we could do is say, for example, we were to pour the green through there. The green we know separates into blue and yellow. So blue might come down here and we'd catch the blue, and then yellow might separate here, so we'd catch the blue, then the solution would go clear, and then we'd end up catching some of the yellow. So we can actually like allow the substances to come through and collect those substances for further testing. So in this case, D is going to be our best answer. Okay. The next one, we have ethyl acetate and butyl acetate. And I know it's kind of hard to read there because I had to make it like skinnier and taller writing. But we've got, so basically, if you look at ethyl acetate and butyl acetate, before we do anything else, you want to see that, hey, we've got this polar structure right here in the middle, and the rest is the only difference, the rest of it is butyl acetate has a longer carbon chain. Okay, that's great, but let's figure out why. So we have a mixture containing equal number moles of ethyl acetate and butyl acetate, and they are separated using distillation. Based on the diagrams above, which of the following identifies the substance that would be initially present in higher concentration in the distillate, and correctly explain why that occurs? So in the distillate, this is the stuff that comes out. Okay, so the distillate is what comes out of solution. So that's going to have this higher vapor pressure. Okay, so it's actually going to have like, it's going to be the part that actually is coming out. So what we want to see here is, first off, we look at ethyl acetate. We have to decide if it's going to be ethyl or butyl. So we need to decide which one is going to be having a higher vapor pressure, which means having actually a lower boiling point, easier to boil. Well, between the two, ethyl acetate is going to boil at a lower boiling point, having a higher vapor pressure, being easier to boil. So it's going to come out higher concentration in the distillate, meaning it's coming out of the distillation, and we're going to be able to separate it that way. So we've narrowed it down to ethyl acetate because, again, the carbon chains are very much different. So then we have to look, ethyl acetate is the reason because it has fewer carbon-carbon bonds to break, or is it the reason because it does have a shorter carbon chain and weaker London dispersion forces? We want to include this in here because we're talking about boiling point, we're talking about vapor pressure, and anytime we want to bring up boiling point, vapor pressure to describe why the distillation comes out, that's what we want to go with. Anytime we talk about, why we want to separate things, how it's separated, the more we can describe with intermolecular forces, the better. So that answer would be B. All right, let's take a look at this one here. We have in paper chromatography experiment, we have a sample of pigment and separated into two components. We've got X and Y. And so the surface of the paper is moderately polar, so that's important to know. What can be concluded about X and Y based on the experimental results? So if our stationary phase is polar, so our stationary phase is polar, and we look at our solvent here, is this a polar or a nonpolar solvent? This is going to be a nonpolar solvent because you've got carbons and hydrogens, and that's about it. And hexane, it's actually going to be a ring, but it's still carbons and hydrogens. So since we have a nonpolar solvent and polar stationary phase, therefore we've got to think about, hey, where is X and Y going to be? So we've got to look at hexane's nonpolar, stationary phase is polar, therefore with the component X being more nonpolar, it's going to go with that hexane. It's going to go with the mobile phase farther. So this one is actually more nonpolar because the mobile phase is taking it farther. The component Y is going to be a little more polar because it's sticking more with the stationary phase and not being able to move as far. So therefore, we know then that Y is more polar than X. This with paper chromatography and so forth has nothing to do with molar masses here, okay? So we're only looking at the polarity. All right, let's look at the final one. So we've got a student obtains a mixture of the liquids of hexane and hexane and octane, which are miscible. That means they can mix and be in an aqueous Which of the following techniques would be best for separating the two components of the mixture and why? So basically, we have a liquid, so if they're miscible, okay? So what we want to look at here is definitely see the differences between the boiling points. We've got a very high boiling point compared to, this is almost half of the boiling point of octane. So therefore, we want to think about with the boiling points, how can we use that boiling point? Well, first off, filtration's not going to work because not one of them solid. They're both liquid. Paper chromatography, the polarity of their molecules, that's not really going to work because look at the formulas here. We've basically got carbon chains. So they're both going to be nonpolar. It's going to be hard to know which is which. Column chromatography, again, has nothing to do with the molar mass. We don't want to worry about the molar mass of the column chromatography. Again, it has everything to do with polarity and the ability to get through like a stationary phase. Finally, distillation, because the liquids would boil at different temperatures owing to the difference in the strength of their intermolecular forces. So therefore, this is going to be our answer because the boiling points are very different. So we're going to be able to set the temperature there, keep it boiling, and be able to boil off we could boil off hexane if we didn't raise it to 126 degrees. If we kept it between 69 and 126 degrees, we could boil off only hexane and leave the octane in the beaker as well without having to actually boil that off. So that's why it's D. All right. So anyway, you guys hang in there. We're doing great. And I hope to talk to you more about this soon. Bye-bye.